put you in a lab. And so I got good at that, and someone said, hey, you're really good with this lab stuff. Let's put you on a computer. And now I use a computer a lot.
Let's formally get started. Welcome. Thank you for coming out tonight. We're excited to have Dr. Nicholas Castle here. He is a research scientist at the Planetary Science Institute in Tucson, Arizona. A graduate of Lehigh, the University of Washington, and the University of Alberta, he has 25 years of experience studying geology, planetary science, and the how-to of space exploration. He's worked with the NASA Jet Propulsion Lab for the past 7 years as a mission operator with the Curiosity rover. An aspiring mission planner, he's developing proposals to study volcanoes on the Earth, the Moon, and Mars. In his spare time, he plays board games, hikes, and plays with his 2 young children. We're going to ask that folks hold their questions till the end. There's going to be a lot of them. And we are filming, so you'll be able to rewatch this and share. You'll see it on Wacam, our local cable access station, and we'll have it on YouTube as well. So welcome, Dr. Castle.
Thank you very much. So thank you for that lovely introduction. As she mentioned, my name is Dr. Nicholas Castle. I'm a research scientist that studies Mars, the Moon, asteroids, and pretty much volcanoes anywhere that I can find them in the solar system. I've been known to give very detailed science talks. That's not what this is. This is based off of my personal passion, which is looking at what we could learn from humans and robots exploring the solar system. So this pretty literally is stuff that I do in my own time, or that I think about in the background while I'm doing my normal paid job. What I do for work is I'm a mission operator with the Curiosity rover. This means that I run one of the instruments and help us analyze the surface of Mars. So I've had a long time to think about what it is that Mars looks like and how we might live there. Over the course of this talk, there's a question I want you to keep in mind, which is, should we live on Mars? The reason why I'm asking this is because before you do anything, particularly something that's hard and risky, you should ask yourself, what's the benefit to doing it? Why is this a thing that we want to do? In the case of space exploration, there have been a lot of direct benefits we've gotten back from doing space exploration. Some of the obvious ones are things like satellites or global telecommunication, even global positioning system. These are all direct returns from the space industry. There are some that are not so obvious though. For example, NASA fueled some of the development of faster and smaller and more reliable computers at a time when a computer usually meant a person who was working with a slide rule to do basic math quickly and efficiently. There have been other things though. For example, did you know that the way that we monitor patients in hospitals is a byproduct of telemetry that was invented to monitor the health of astronauts in the Mercury program that continued through to Gemini and Apollo? That whole notion of electronic devices that monitor a human's health is something that was developed for the space industry that we found other uses for, and now is the basis of how we assess modern medicine. There have been a number of other advances along those lines, and that's in the past of space exploration. So the question is, if we were to do something truly outrageous, like trying to send people to live on Mars, what might we learn from that? So, the content of this talk, we're going to go through what is it that's so difficult about Mars? I mean, there's the obvious. We're a life form that evolved on Earth, evolved in this climate, evolved to be amenable to this climate. Mars is a whole other climate, a whole other planet with a whole other history. There will be challenges in adapting something built for one thing into something else. But why are those challenges, and what are some of those challenges? That's where we're going to start with this. We'll then transition to say, okay, knowing these challenges, how might we overcome each of them in turn? And what would that make living there look like if we're trying to overcome each of these things? From there, we'll naturally move into a question of, well, if we're going to live someplace, we better be able to produce some of the things we need, so that we're not always importing everything we need to sustain ourselves. That's the question of industry. What does industry look like when we go to another planet? And then we'll wrap it all back up at the end to say, what is it that we have, that we could learn from doing this that would be of use back here on Earth? Everyone with me? Great. So, what do we know about Mars? The very first thing that I would say is this has been talked about a lot in the media. particularly going back about 5 years ago, where Elon Musk was talking a great deal about, we'll solve the population problem on Earth by sending everyone to Mars. The Atlantic wrote an article that, at least in my field, was somewhat influential, that pointed out, this is a ridiculous idea. Mars is a hellhole. Their words, not mine, although I happen to agree with them. It's a difficult climate. It's really cold. There are other problems we'll get to. And their conclusion was, this is a ridiculous way to solve our problems on Earth. And if you think the solution is, we have too many people on Earth, let's move them all to Mars, they're absolutely correct. It is way too difficult to send literally billions of people from one planet to another to solve the problem of there are too many people on this planet. But there may be other ways that we could use what we learn from getting to Mars, from being on Mars, from doing things there, that would be of benefit back here on Earth. I'll leave it to you to decide whether I'm right or they are, or if there's some other answer entirely. But that's kind of where we're going with all of this. So, would it surprise you if I told you that the fundamental problem of Mars is that Mars is small? Now, if a scientist stands up and says something like Mars is small, your first question should be what does that mean? What does it mean when I say a planet is small? Well, let's answer that. These are the terrestrial planets drawn to scale. Going from order of the sun, we've got Mercury, Venus, Earth, and Mars. Mars is one of the two smaller ones. Its radius is a little bit larger than Mercury, but Mercury has more mass, so they're about the same. Venus and Earth are about the same. And this is what I mean when I say Mars is small. It's much, much smaller than the Earth. Now, those of you who have been to an astronomy lecture before might say, no, wait a second. How does the moon fit into this picture? Is it smaller, larger, about the same as Mars? Well, here's the moon shown to scale. So it's larger than the moon, smaller than Earth. Another way to look at this would be to talk about gravity. Earth has 1g is our gravity. We defined it that way. Mars has 1/3 of a g. The moon has 1/10 of a g. That's about right for thinking how big are these things. Those of you, by the way, who have been to far too many lectures on astronomy may want to tell me, but wait a second, doesn't Mars have moons? It does. It has 2 moons. Shall I show you those to scale? Here's Phobos. Everyone see that pixel? Deimos is even smaller, so I didn't even bother. It doesn't show up at the screen resolution. These didn't form through the same kind of processes as Earth's moon. They're likely captured asteroids, they're teeny tiny bits of rock, and they're not going to be the same benefit to Mars as the moon is to the Earth, particularly if we're trying to go out and explore space and live there. If you're curious about how this lines up in the rest of the solar system, here's the whole solar system, again, roughly on about the right size scale. Those numbers that I've put up there are the mass of the different objects proportional. So if you set our solar system as the sun, you'll get a 99.86 on that exam. Our solar system is almost entirely the sun. The error in what I just said is Jupiter. The error on that is Saturn. There isn't a lot of mass in the things we're talking about, but these are the kinds of places that humans could live, so that's why we talk about them as so important. So, getting back off of this tangent and asking the question of, well, why is Mars being small such a problem? Let's look back at the Earth and talk about what it is about the Earth and something called cooling rate and magnetohydrodynamics. Don't worry, I'll get there. This is a cross-section of the Earth, what my wife is very fond of calling the everlasting gobstopper model of the Earth. All we're talking about is these are the different layers. On the outside, you've got an atmosphere, then you've got the crust, which is what we all walk on. The inside of that is the mantle, which is where Earth's rocks mostly come from. Beneath that is the core. And that's one of the most important parts for this story that I'm about to tell. It's got an outer core, which is liquid, and an inner core, which is solid. Now, you may be distracted at this point by the question of, what is that word magnetohydrodynamics? This is not a massive science talk, so I'm not going to go ahead and define that. Instead, I'm going to take a page from the webcomic author Randall Munroe, and I'm going to refer to that as magic. Anytime you hear magnetohydrodynamics, just say, ah, yes, the force of magic. Well, what's going on is the Earth's inner core is actually floating relative to the rest of the planet, so it has a slightly different spin rate. This allows, through the force of magic, the creation of a magnetic field. Why is a magnetic field important for the Earth? Because the sun is trying to steal our atmosphere. The sun creates a solar wind, which consists of, among other things, a lot of charged particles. When those hit the magnetic field of the Earth, they deflect around the Earth, and they go elsewhere. Now let's look at Mars to see if we can figure out what the problem here is. On the same scale, here's Mars. That's a whole lot smaller. It's got the same kind of layers as the Earth, an atmosphere which is really quite thin, a crust which is thicker, a mantle, and a core. But the problem is Mars is so small, that core has almost entirely solidified. Whatever liquid is left isn't enough to float the inner core, so there's no difference in the rotation, and it doesn't make a magnetic field anymore. It used to. It had a magnetic field that protected it, but once it cooled down enough that the inner core wasn't floating, the magic stopped and the magnetic field went away. At that point, the solar wind could directly impact Mars. And when it did, it created a process called atmospheric spallation. Don't worry, I'm going to stop using jargon, I promise, one of these days, I swear. But in the meantime, all that means is that the sun stripped away inexorably and very slowly the water content of Mars, the atmosphere of Mars, nitrogen, carbon dioxide, pretty much everything that was there, the sun is slowly taking out one piece at a time. The first major effect of that was losing its water. It lost its oceans. At which point, you can picture every sandy beach on Earth without an ocean nearby. What happens? The surface becomes dry and dusty. You literally have sand that used to be on shores that's now being blown around the planet for a few billion years. That's a lot of dust. The next problem is that atmosphere itself. You see, when an atmosphere comes about, it's because of a competition between volcanoes that are blowing out volcanic gases from the inside of the planet and everything that's happening on that planet. In the case of Earth, a lot of that's the weathering of rocks. Carbon dioxide from volcanoes attacks rocks and slowly makes carbonates, those big limestone deposits we have on the shores. That ultimately started with weathering rocks. Life got involved, started making shells out of that, and that became large deposits of limestone. And then remaining algae and plant life attacked what was left and converted it to oxygen. And what's left on Earth is a whole bunch of nitrogen that largely didn't go anywhere. That's why the Earth has such a funny composition for its atmosphere compared to anywhere else. Mars, on the other hand, wasn't able to keep collecting that stuff. It kept getting stripped away by the sun. So its atmosphere that it has is more or less volcanic gases. It's directly what volcanoes erupt, which is a lot of carbon dioxide, and not a whole lot else left. Now, if I really want to make this plot, true to form, I'm going to show you the same pressure between both places. It's a competition between how fast can the volcanoes erupt gases and how quickly can the sun steal it back away to bring it anywhere else. And the volcanoes are losing. There's not a lot of pressure left on Mars. If Earth's atmosphere is 1 bar, Mars's is 0.006 bar, or 0.6% of Earth's atmospheric pressure. You'd be forgiven for calling that a vacuum because it basically is. Now there's one more problem, and that's that it's not just the sun that's trying to kill you. Turns out the galaxy itself also kind of wants to see you dead. And this creates a problem with radiation. Galactic background radiation creates cosmic rays. These are high energy gamma rays that come in. When they hit an atmosphere, they tend to create ionizing radiation, or bad radiation. These happen at enough energy that then tends to hit more molecules in the atmosphere, splits them and makes more and more and more. This is what's called a radiation cascade. In the Earth, this happens in the extreme upper atmosphere. It's only really a problem if you take a lot of intercontinental flights, where you've got a very high cruising altitude, and you get a modest radiation dose every single time you do that. Don't worry, OSHA says it's safe unless you live there. Mars, on the other hand, that radiation cascade peaks around the surface. So the surface is getting about as irradiated as it can be, just because the atmosphere is so thin. All right, so let's summarize these problems. Mars is small, which isn't just a problem for gravity. It's a problem because it cooled and lost its magnetic field. And that made Mars dry, which inevitably also made it dusty. What atmosphere is left is toxic. It's mostly carbon dioxide, which wouldn't be great to try to breathe. And the surface is irradiated. So these are the problems that we would face And this, by the way, is a short list, a simplified list. There's more, but we'll start with this because it's bad enough. This kind of proves the Atlantic's point that Mars is a hellhole. It's very hostile to human life. So, what would it look like if we tried to live on Mars? Well, let's start off by thinking about what do you need as a human to survive somewhere? Well, there's kind of three things you're looking at. You need food and water, you need a place to live, and you need clothes to wear. We're going to get to all of these things, but we're going to start with one of the easiest ones to talk through, which is what would your shelter look like? How would you live on the surface? Well, a lot of people talk about visiting Mars as though it were the Apollo program. And that inevitably means your spacecraft flies by, eventually lands, and you probably inflate some of habitat on the surface. I designed this doodle myself, but it's pretty much The Martian. And for what The Martian was talking about, it's basically right. It's an inflatable habitat on the surface. But we're not talking visiting. We're not talking 30 days. We're talking living there, which means that cosmic radiation is going to be a problem because you're getting dosed by radiation hitting the surface. I forgot to mention, the surface of Mars hits about 23 rem, surface of Earth hits about 0.3. That's a kind of arbitrary scale where 100 is about the point where acute radiation sickness sets in. OSHA says you can work with about 20 rem, so we're a little above what OSHA would like you to see. That means you don't want to live in that all the time. You're going to have problems eventually. So what's the solution to that? Turns out there's a pretty easy one. Bury your house. If you bury your house underneath just 8 meters of crushed up rock, literally the regolith of the surface, you're insulated. That radiation stops in those 8 meters. You just need a little material between you and the surface. Okay, next problem. Mars doesn't have much of an atmospheric pressure, which means you're living inside of a high pressure vessel. Pressure vessels do not like corners. So you're not going to make a house like you would on Earth, where you've got a nice cube or rectangular prism. You're going to try to round out those corners because those are your most likely points of failure, which means you're living in a sphere. You may still have floors on that. You may subdivide that depending upon how big your bubble is, but you want that kind of shape to be able to fit things in and have the lowest chance of a catastrophic failure. Now, it's not enough to just live in a bubble. You also need to get to the surface, right? So you're going to have some sort of surface access that's coming into your tube. Now, what was one of the other problems for Mars? Oh yeah, it's dusty. Well, the surface is covered in dust. And by the way, when I talk about dust, it's actually doing it a bit of a disservice on Mars. It's a lot like if I went to a nice, beautiful sandy beach, the kind you love to build castles in, and called that gravel. This dust is so fine, talcum powder looks coarse. This is the kind of, we would actually geologically call it fines, that are so thin, they're going to go through most pressure seals you would have. So an important thing to do between your settlement and your surface is to have a really good airlock. And it's probably not just an airlock. You're probably talking about everything that goes outside doesn't come in any further than this. You're talking about changing out your spacesuits. You're talking about doing your cleaning, talking about taking showers before you even go into the rest of your settlement, or this fines, these dust particles, are going to be everywhere. And that's a problem just by a physical hazard, but they're also a bit chemically active, which is another problem for humans. That also means you're going to want to limit how much you're doing outside. So you're going to put an emphasis on teleoperations or communications to be able to operate things without having to go out into that environment yourself. So that's kind of our image of what a house might look like on Mars. You've got a bubble with an air tube, and then an access point that's heavily focused on cleaning. And then communications for everything that you can possibly do outside. Well, this looks a lot like a modern house, so the next question is, doesn't it need electricity? How are you going to power this? Well, one of the most common things you see in science fiction is to talk about solar power. You might have an array like this. That's great. Solar power is clean, free energy. As long as the sun is shining, it's producing power. Couple problems with it though. First one is the common problem cited for solar power. Nighttime exists. Okay, we can probably solve that with some form of battery, but does cut down how useful these solar panels are going to be. The next problem is dust. On Earth, we don't worry about this very much, but there's so much more of it on Mars, this can coat your solar panel and diminish how much power it can possibly generate. The third problem is a little less obvious, and that's the irradiation problem. Solar panels gradually decay, and it's mostly because a high-energy particle hits it. And the way a solar power panel works is it's a dipole that takes in a photon of light and moves an electron along. That's generating power. If you hit that with radiation, you can flip the dipole so it takes in power and emits infrared light. If you look at an old solar panel that's been sitting around for a while, it glows in the infrared because it's slowly had individual little cells flip from producing power to using it. And that's based off of how much radiation is hitting it, for how quickly that occurs. Now, one other problem, because Mars is, well, a bit of a pain, it's twice as far away from the sun as the Earth is. Your power density falls off with the square of distance. It's based on the surface area of a sphere. If it's twice the radius, it's a quarter the intensity. So you need 4 times as many solar panels to get the same use that you would on Mars as you would on the Earth. Everyone with me on that? So there's problems with solar power on Mars. Well, what's a common green energy that people talk about as a replacement for solar panels, one of its chief competitors? Courtney here is doing the spiral motion, which means wind. Yes, wind power is a common alternative we talk about. Couple problems with, well, first, its pros. As long as it's windy, you've got power. That means it works at night, which is great because you don't have that same kind of downtime. The problem is, once again, the dust. These are mechanical systems with moving parts. Dust loves to find its way into a moving part, which increases wear. That means you're going to have to maintain these more often. They're also more complex than something like solar panels, so that also increases your maintenance, which means you're going to have to be on the surface more often with wind power. But Mars being a pain in the butt, there's one more problem. Remember how we said Mars doesn't have much atmosphere? That lowers the power density of your wind. So yes, you can engineer for that, but if the power is not there, you can't get more than is present. And there isn't a lot of power in Martian wind. So it will work some, but it's not going to be the be-all end-all, just like many other environmental techniques wouldn't necessarily work unless you find just the right place on Mars. Which means a lot of people like to talk about one more alternative. Nuclear power. Everyone love nuclear power? Excellent, me too. It's a wonderful, steady power source. It can make quite a bit of power. The problem is, there aren't likely to be large ore deposits on Mars. A lot of Earth's ore deposits ultimately owe their existence to plate tectonics. This is the process where the surface of the Earth recycles itself back and forth through the mantle, and that works like a distillation column where it takes some of the stuff that's not common and concentrates it at the surface. That ultimately leads to ores. It's more complicated than that, but that's the basic version. Mars doesn't have that, so uranium ore isn't going to be there, which means you're always going to have to import this as a fuel material if this is what you're relying upon, which means you can never be self-sustaining. That's a problem. So how are we going to do it? The answer is, honestly, probably a mixture of all three, plus anything else that happens to be circumstantially possible. If you're near a volcano, you might have enough geothermal power or geothermal flux to make a geothermal power plant. You might have a few other things like that. But it's going to be very difficult to power wherever you choose to live. And whatever the case, you're going to have shortfalls, which means you need to invest seriously in batteries to help you get through those lean times, whether it's solar power at night, or wind turbines when the wind isn't blowing, or nuclear power when your shipment just didn't come in time. That doesn't necessarily mean lithium ion. There are a lot of alternatives for that, but you're going to have to get good at doing that if you're going to have reliable power on Mars. And by the way, you'll die without it. Okay, now that we've talked about all the fun bits of how we might live there, what are we going to do there? Well, one of the first problems is we kind of want to eat and drink. So, where would we find water on Mars? One of the places we know water exists is at the poles. Mars has two polar caps, a larger one in the northern hemisphere and a smaller one in the southern hemisphere, and they're interlayered back and forth between water ice and dry ice. We even know about how much water ice is there, so that's a great source. It's quite a bit of water. It's also relatively pure, because this all came directly out of the atmosphere and is just sitting there. This is awesome for us. There's also permafrost. Some of our landers have seen this when we've dug through with scoops, and there's some geologic evidence, things like scalloped terrain, which indicates there was a lot of permafrost that's been slowly sublimating. We see this stuff on Earth, and we can see its analog on Mars, or at least we're pretty sure we can. So we're pretty sure there's quite a bit of permafrost. There are also glaciers on Mars, which means odds are there's buried ice. In New England, we talk about kettle ponds. These are places where there were more rains, a big chunk of ice got buried, time went on, things heated up, that ice melted, sublimated, did its thing, and we're left with a lake. So we're familiar with this phenomenon. The problem is, we don't know where that would be on Mars. We've got some evidence of glaciation, which means it could be there, but we haven't seen it, because you'd have to prospect for it. And then there's this idea of a subsurface cold trap. Literally all I'm talking about is a cave system with a skylight. So you talk about things like a lava tube, you poke a little hole in it, everything in the cave doesn't see sunlight, so it's really cold. Well, at one point in time, there's a bunch of water in Mars's atmosphere, and there still is a little bit. And so that could slowly accumulate more and more ice as time goes on as just being a cold place where ice comes in and never leaves. So, what are the problems? The pro of polar ice caps, we know it's there. The problem? How easy is it to live at the North or South Pole? Not easy, for so many reasons. So this is a hard source to access just because of where it is. Permafrost? Well, that's usually interlayered back and forth with sediment, those silts and fines, which means this is going to be chemically mixed bag. There may be a lot of ice there, but you're going to have to do a lot to get that to the point where you can use it. Buried ice? This could be very pure, but we'd have to prospect and find it the same way we do for oil on Earth. You have to actually go there and ground truth. This is definitely present before you can say it is. We suspect it's there. We don't know it's there. Same idea with these cold traps and caves. We actually need to find skylights, what we would call pits if it were on the moon, to find these caves that can trap this ice. We don't really know of many of these. And we certainly haven't been down into them to see, is there actually ice there? So we can probably find water, but it may be very difficult. But let's assume we can find water. How are you going to grow stuff? A lot of people, when they talk agriculture, start talking about, well, what would a greenhouse look like? You can plop it on the surface, but you've got a few problems there. It's irradiated, it's cold, there's also not nearly as much sunlight as you're used to, and it can get covered in dust. You can solve that by moving it inside, but then you need grow lamps, and remember how efficient solar power is and how precious power is? Well, that's another problem. You might even come up with clever solutions like, let's bury the greenhouse a little bit and use a lot of mirrors in a way that keeps us from being so susceptible to dust. But, okay, you might be able to engineer a clever solution, but the fundamental problem is actually with how do we grow stuff on Mars? So let's look a little more closely at that. Here is my little doodle of a humble tomato plant. What would it look like to farm? Well, the goal of farming is you put in sunlight, you take out food, right? Simple model. Everything works brilliantly. First problem. Mars has a lot less sunlight than we're used to on the Earth. Okay, you can probably engineer your way around that. So let's move on and talk about what's going on. Plant takes in carbon dioxide, which is great. That's helpful for whatever settlement we've got. Plus we can add more if we need to from the atmosphere. Awesome. As an added bonus, oxygen comes out. Those of you who've taken a course in botany or ecology or bioscience of any sort know water's also involved in this process. Well, we said we had water, so that works. But there's a few other things missing from this. Who here's ever done gardening and worked with a combination of plants called the Three Sisters? This was a common indigenous practice in the Southwest where they had corn and beans and a squash. And they would plant the three of them together because they found that did a whole lot better than those three plants separated. A good illustration of why comes in the discussion of what does corn take from the soil? Nitrogen. And beans adds to the soil nitrogen. And so one of them removes from the soil what the other one puts there. Well, that brings up the question of, what are we going to do about nitrogen on Mars? There's a similar problem with phosphorus that would take longer and someone with a different PhD to explain. You're going to need these things, and on on Earth, nitrogen comes from the atmosphere, which ultimately is from volcanic outgassing. But it's just a little tiny bit of what volcanoes blow out. And remember, Mars has lost most of its atmosphere. It hasn't accumulated for 4 billion years like the Earth has. So there's only that teeny tiny bit that the recent volcanoes have added. So nitrogen is going to be a problem. We also don't have a lot of minerals that hold a whole bunch of nitrogen in their structure. So there isn't a mining way to mine your way out of this problem. You just don't have much nitrogen there. So you're always going to need to import it from somewhere and take really good care of what you've got. Phosphorus on Earth has accumulated from the weathering of rocks. There's a little bit of phosphorus in the form of phosphates like apatite in most volcanic rocks. On Earth, that stuff tends to end up in oceans, which tends to find its way into life. Big deposits of phosphorus on Earth come from fish skeletons. There are shallow seas and a ton of fish lived there. Their skeletons piled up as they died, and that made a big rock. Same kind of way limestone works off of clamshells. Phosphates come from fish skeletons, mostly. Florida is a great producer of phosphorus, if you're curious, in the US. And it's exactly that. It was a shallow sea, many years of fish was piled up and made those rocks that form the center of Florida. Well, we've got a little bit of phosphorus in volcanic rocks on Mars, but it was famously lacking in fish. And so we don't have these great big phosphate deposits to be able to mine to get that. And these two examples paint a picture of there being a much larger problem that's going on here, which is there's a whole lot of soil mineralogy, magnesium, iron, calcium, just to name a few major ones. There's a lot that plants extract, even in small amounts, from the soil that's all over the Earth. So let's plant this in Mars rocks. Well, sorry, Mars soil. There's a problem with that. We don't have Mars soil. Mars has rocks, not soil. Soil is a combination of complex biochemistry, active biology, and a bunch of other processes that are breaking down bits of rock. It's an active ecosystem, not rock dust. Mars has rock dust. Well, we might be able to make Martian soil if we incorporate little bits of rocks from the surface into things like compost. And this produces silicate weathering, which is the process that releases these elements that plants need. Now, famously, there are a few other problems with Martian rocks. For example, perchlorates, which are terribly wonderful for life, as in they oxidize life. It's really bad for life. So there's going to need to be some pre-processing. I put together this whole picture not to show you this is a solved, simple problem of agriculture. This is a simplified picture of what agriculture would look like if you really tried to do it at scale. And you see how messy and complicated that is? Every problem on Mars is going to be this kind of messy and complicated. And there will be way more details than you want to think about with each and every one of them. But if we're going to do this kind of stuff, you're talking about building an industrial process. You're talking about something that involves a lot of tubing, a lot of containers, a lot of basins. And so you need a way to make the containers and the piping that you're going to need to do this kind of process. Put another way, we need plastics. Anyone know how we make plastics on Earth? From oil. We mine oil and we use long-chain hydrocarbons to turn them into plastics by polymerizing them. Mars doesn't have that, but we might still be able to make it. A famous reaction that people talk about on Mars is combining carbon dioxide with hydrogen to make water and methane. Methane in this equation is the important part because that's rocket fuel. It's a stable thing that you can use as the fuel combined with oxygen to burn and make rocket propellant. Elon Musk is designing Starship around methane, specifically with this in mind, because we've had for about 40 years now the idea, if we send a bunch of water to Mars, we can do this reaction and make rocket fuel. Well, how does that work? Well, first off, carbon dioxide is just Martian atmosphere. We compressed it, maybe we kept the sediment out of it, but it's just Martian air. To get the hydrogen, you take water and you electrolyze it. That means you made an electric cell where at the anode you're producing hydrogen, the cathode you're producing oxygen, just splitting oxygen into its two component pieces. Oxygen's great because you've got other uses for that, like breathing. Hydrogen you'd want to put into a process like this, where you're making that methane. And so you get yourself a nice big chemical reactor and you produce methane from the atmosphere by splitting water. Well, what else can we do with this? It turns out it's possible to stick two methanes together and then desaturate it to make something that's called acetylene. Who here knows the chemical name acetylene? Why do you know acetylene? Acetylene works as a torch. This is a hot burning material that you can use for cutting metal. And so this is an important thing to be able to make if you're going to do construction. You can also use those same temperatures at a lower intensity to weld stuff together. So this is a great fuel if you're trying to build things out of metal. But it's more than that. It turns out acetylene can be a feedstock into a radical polymerization process where you convert that into plastics. It's not quite as simple as that makes it sound, but that's your idea. You put another chemical reactor that converts this into plastic. Well, now I just showed you how to take water and Martian atmosphere and make plastic. Plastic, by the way, is good for synthetic clothing if you're not able to raise sheep or grow cotton or do any other process. And a lot of what you're wearing contains plastics of various varieties. But there's something else really cool that you can do if you've got acetylene as a feedstock, which is you can convert that into pharmaceuticals. You can use that as a base hydrocarbon with a lot of chemical potential to turn into larger hydrocarbons and get the whole of organic chemistry out of it. It is not easy. It is mind-bogglingly hard. But if you combine this with the other elements that you would need, nitrogen again, sulfur, phosphorus, all the kinds of stuff in modern pharmacochemistry, you can get there with great difficulty. It's possible, not easy. So that's a picture of what you might do with water and Martian atmosphere that gets you plastics and starts to get you into modern life as we know it. The problem with a lot of this, though, is this is very power intensive. So are there solutions we can use to lower the power requirement of this? And one notion is to directly use the power of the sun and make something called a solar furnace. Who here's ever heard of a solar oven? Solar oven's just basically a black box with a clear lid that works like a greenhouse that's just intended to keep running away with temperature. You're doing the same kind of idea here. You take a ball of water with some absorbent material on one side and clear plastic on the other, and you raise that up so it can be a target. Then you build a whole series of mirrors around it so that you can deflect sunlight directly into that ball of water and heat it up a lot. It turns out if you get water hot enough, and my apologies, I've forgotten the temperature, but water starts to spontaneously split into its component atoms. It doesn't just boil, it breaks down as a molecule. Well, it doesn't just stay that way, it starts to recombine, and sometimes when it does that, it makes hydrogen and oxygen. It spontaneously splits if you get enough sunlight concentrated on a spot. Well, if you do that, you can cool down the gases that come out of there and start collecting hydrogen and oxygen just from sunlight. That's one example of how you could do that. So now we've talked about a lot of different buildings you'd want to build. The structure you're living in, an agri-dome for where you're growing your food, industry, you're talking about solar furnace. How do we build on Mars? This is a big problem. If we're going to ask that question, it's fair to say, well, okay, how do we build on Earth? Turns out there are a number of different ways. Sometimes we use wood or bamboo or similar. Sometimes we use plastic, glass, metal, bricks, concrete. These are all options for building on Earth. So let's talk about them on Mars. The problem with wood or bamboo or any number of plant-based options is you're removing biomass from your agriculture that I had just spent a while telling you was precious and hard to do to build your buildings. This is not a good competition to have. Plastic Same idea. You're taking a bunch of power and water and you're dedicating it to making something just to build more buildings. Again, this is a problem because you're exploiting a limited resource. Let me tell you, as someone who doesn't want to live in a glass house, I really don't want to live in a glass pressure vessel. So, although you can easily make glass on Mars, you might not want to live there. Bricks, you can actually make those fairly easily, and there are a number of ways people have talked about, everything from literally making adobe to, which is bricks made out of straw, human waste, etc., pressed together and baked. Or you could take just ground up bunches of sand and fines, heat them up to the point that they fuse and make a glass brick. That's awesome if you've got bricks, except remember where you need to live in a pressure vessel? You need something to stick those bricks together, which means you're probably relying upon concrete. And you're in good company. On Earth, something like 95% of built structures today, worldwide, rely upon concrete. That's a lot. Well, what is concrete? It's a mixture of cement, about 10%, ground up rock bits, which is 80%, tons of that on Mars, by the way, and water, about 10%. Well, let's look at how that process works. You start with limestone. You mix it with some clay, you heat the thing up, and you make what's called a calcium silicon oxygen binder. It's actually a mix of 4 major compounds and a bunch of other stuff that I really don't want to talk about because I'm not a cement expert and it would take a really long time. But suffice it to say, you can combine these two things, heat it up, and make cement. That's awesome, right? We can just do that anywhere. Except, remember where I mentioned that limestones come from clamshells and similar things accumulating in the ocean? Whoops. We do have limestone on Mars, but it's not great big deposits like there are in the Earth. There's a little bit here and a little bit there in a few places. So it's not a major thing you can get. Clay, unfortunately, same problem. There's a little bit of clay here, a little bit of clay there, but it's always mixed in with other stuff. It's not these great big massive deposits like we have on the Earth. And if you can't get the two components to make it, you can't make cement. So what are we going to do instead? Well, some brilliant researchers said, well, what if we just change the material that we're making our glue out of? And they came up with a concept that they call Marscrete. And literally all they did is they said, what if it's magnesium instead of calcium and the similar sort of compounds? And it turns out they can make this stuff. One way to make it is to use magnesite, which is magnesium carbonate. Combine it with clay, but we run into the same problem there. And so they said, well, this is how we made it in our lab. This is how we tested it and know that it works just like concrete. But it's not going to be a viable source on Mars. How would we do this on Mars? Turns out basalt has a lot of the same elements you need for that. And the way you get there is you induce it to weather. You do the same thing Earth would do in nature, but you do it really fast on an industrial process, which we're still sorting out how to do. But if we get good at it, you could start to make Marscrete, which is the component of Mars cement. Now, it's not just that you're making this magnesium silicon oxygen binder, you're also weathering the rock, which means you're making iron carbonates, magnesium carbonates, and calcium carbonate. You're also leaving behind residue in the form of silicates, silicon oxides, aluminum oxides, which are also going to be useful. For example, if you want to make solar panels, having a lot of silicon oxide, brilliant. That's what you need. So this process helps feed into other industries as well, and the carbonates may form metal feedstocks and for processes to isolate the metal, because you're reproducing what Earth did fundamentally to make ore deposits, except now you're doing it yourself in industry by mixing water, carbon dioxide, and a lot of heat into basic rocks and reproducing that weathering stream. Well, this is where the question gets a little bit interesting in terms of what happens back on Earth. On Earth, making cement accounts for 10 to 15% of global CO2 emissions. If we replaced it with Marscrete, you wouldn't have those emissions because a lot of that comes from breaking down your limestone. And here you're dealing with basalt, not limestone, so you're not producing CO2 in the process. As a matter of fact, you're actually taking it in. And one of the cool parts about that is magnesium carbonate, which you would produce in this process, is a geologically stable way of storing carbonate from the atmosphere. In fact, given billions of years, it's what nature will do with the CO2 we've already put in the atmosphere from breaking down rocks like basalt. But it takes millions or billions of years to get there. We're just saying, let's figure out how to do it with industry. So one of the cool benefits by imitating Earth's weathering process is we might have a way to help solve climate change. All because we asked the question of, but I want to build stuff on Mars. So let's go back to our picture of what do we need to survive. We've talked about food and water, shelter. We even mentioned clothing along the way. We've even gone beyond that, though, and talked about we need to build more than just a person living on the surface. We need a lot of people. So companionship, society, building a place for a lot of folks to do things. And we have plenty of things for those people to do, which is fulfillment. It's a job that seems worthwhile. And ultimately, there are places where that technology might return and be of benefit back on Earth, which is an aspiration, something people want to work towards. So what can we learn from settling Mars? The first thing is, we need power to work well. So we might very well learn how to be better at green energy. Whether that's solar panels, wind turbines, geothermal, you name it, that power is precious and has to work without a lot of waste. We may also figure out better how to do things like directly use sunlight in industry. Because power is so precious there, well, we could bring that back to Earth and do the same thing here. In fact, there are actually companies that are working on solar smelters for water with the ultimate intention of smelting ore with it. All of this process, including creating pharmacochemistry out of carbon dioxide, could help us lower our dependence on fossil fuels as a planet. And so this could help move us away from petroleum chemistry if we worked on it and got good at it, as we would have to if we're going to survive on Mars. We could also look at alternative building materials, which themselves lowers our carbon footprint. And that could also lead to enhanced ore mining. All of those extra carbonate byproducts become ores that we need, whether that's iron or magnesium or actually critical materials like rare earth elements. All of those can be brought out of basalt if it's done well. But that's a big if. So, there's my whole presentation. Sorry I ran about 2 minutes over. So are there any questions? Yeah.
I've got this science question to start off. Right at the beginning, you showed the composition of Mars, the core, the mantle, blah, blah, blah. How do we figure that out?
So the question is, right at the beginning, I showed the internal structure of Mars. And how in the world did we figure that out? Here's that plot. The answer is it's complicated, because I'm a scientist. Everything is complicated. A little more detailed answer is we figured out there's a core because we've orbited Mars in such a way that we can get some of the density structure based off of orbital resonance. We've also landed a seismometer on Mars, which is a very impressive achievement. And with a single point seismometer, you can pull out gross level internal structure. And that's let us get a pretty accurate measurement of the size of the core and whether it's liquid or solid. Turns out shear waves and compressional waves travel differently, and seismology is a mess. But you can by doing that. We've also got a lot of compositional models which feed into thermodynamic models that look at the internal structure. But you really want to talk to a geophysicist about that one, and I'm unfortunately a geochemist for that conversation. And will definitely hide in geochemistry rather than talk about geophysics. Did that answer your question? Okay.
You haven't talked at all about a microbiome and how could we potentially seed a microbiome and sustain and grow a microbiome to support life.
So the question is, the statement is that I didn't talk much about a microbiome, and the question is, how might we create a microbiome on Mars, sustain it, and grow it? And that's an excellent question, and there's a very good reason I didn't go into any level of detail on that. I don't study microbiology, so I don't know how to unpack that in a realistic way. The furthest I mentioned it was talking about we don't have soil on Mars, and we'd have to create that. I'm aware it's a problem. I'm aware of the need for it. I don't know how to do it. I think there are people that do have some notions on that by doing things like...
Astrobiology.
There's a lot of astrobiology. So the basic idea is you're going to want rock bits going into biochemistry and having a microbiome associated with that. The Martian talked about this for literally mixing up ground up rock surface. He scooped up the regolith of Mars and mixed it with human waste. That's not a bad start. Mixing that with plant matter waste would help that a great deal more. But something that would be really important if you're going to live there is pre-prepping that soil before you do that. And that's because you want to strip out things that are harmful to plants and life in general, like perchlorates, which are carcinogens. The effect of a perchlorate is to break down organic molecules pretty well because it's a strong oxidizer. That's part of the results of the Viking experiments for how we identify these things. You got to get rid of that before you start trying to make soil out of it. It's going to be hard. Yeah, sorry. I know that didn't quite answer your question, but you're right. It's a big problem.
Questions is good.
Yeah.
Getting back to the core, if it's not moving, then it's a dead issue. Why are we focused on Mars at all? It's too small of a planet. It's a non-starter.
So the question is, if the inner core of Mars isn't floating and generating a magnetic field, you'll never fix that problem for Mars. So why are we focusing on Mars? Because it's a dead issue. I love the pun there because that also kind of means it's geologically dead, but that's another story. Well, I've argued about this one a lot with friends, and it really boils down to, where would you prefer? The moon doesn't have an atmosphere. Okay. Sorry, we have a provocateur here with Venus would be a better place to live. So oftentimes people make a debate between the moon and Mars. And the moon is a brilliant place to try to live, but it's not going to be a place that's sustainable for long-term human civilization without the existence of trade. And the reason why is because it doesn't have an atmosphere. So a lot of that atmospheric chemistry isn't going to happen on the moon. There are too many things you have to import to the moon to keep civilization going there for it to be sustainable without trade elsewhere. You're always going to have imports. Venus is an interesting notion because it does have an atmosphere. Way too much of an atmosphere. The surface pressure is so high it makes the Titan submersible look like a wimp. It also has a surface temperature so hot, it's going to melt most metals that you're going to put into that. So you really can't engineer a submarine that's going to get down to the surface worth a darn. The Soviets actually tried this quite a few times, and I think their record was something like 23 minutes before their entire lander, which was built like a shot put on steroids, had catastrophic failure. Venus is going to be really hard. And we're not talking about terraforming. That's someone else's field. I love that field, but it's for board games, not for current engineering and science. If you're going to live on Venus, you're living in the clouds. And there's problems with that. For example, some of those clouds on Venus are sulfuric acid. And I don't mean a nice dilute solution. I mean sulfuric acid, the molecule. As in, it gets wet, it eats through your metal. Enjoy! And that's at about where the pressure and temperature are about right for humans to live at. So Venus has problems. Mercury also has water at its poles in permanently shaded craters. It's unfortunately locked in orbital resonance with the sun, and not a nice 1-to-1 where one side gets fried and the other side stays cold, and you could have a nice civilization on that band. It's in a 2-to-3 orbital resonance, which means you get very slowly charbroiled as the planet very slowly turns. It's not a happy place to live. Maybe at the poles, But we're not talking billions of people, at least not with what we currently understand as engineering technology. You want to talk about Enceladus? You're nicely far into Saturn's wonderful ionic radiation belts, the Van Allen belts. Similar idea with Europa. It's not directly in one, but you know what the biggest thing inside the solar system is? Jupiter's magnetic field. The solar system is defined by the sun's magnetic field. The next biggest thing is Jupiter's. And your size of your radiation belt and their intensity is proportional to how big and strong that magnetic field is. I do not want to fly in and out of Jupiter's anything, because I'm afraid I will turn into a goo. So that one's going to be really hard. You get to places like Titan, which is Earth-sized, reasonable gravity, except it's way further out, orbiting Saturn. Similar problems with radiation. It's also got an organic molecule atmosphere that will happily dissolve your composition. So it's very difficult to think about how you could live there. So really, I keep coming back to the question of, where else? Mars is a hellhole. The rest of the solar system's worse.
A question from online.
Yeah.
How long would it take Earthlings to reach Mars, and what conditions would they be in when they arrive?
So the question is, how long would it take Earthlings to reach Mars, and what condition would they be in when they arrive? Excellent question. The lowest energy way to get to Mars is what's called a Hohmann transfer orbit. The easiest way to think about it, although it's a little more complicated than this, is if you take the average of the two orbital periods, and a half period transfers from one orbit to the other. Earth's orbit is 1 year long. Mars's orbit is 2 years long. That means the average is 1.5 years, and you're going halfway, because you don't want to come all the way back. You just want to stop at Mars. So 9 months. That's a ballpark way of thinking about it. And there's your Hohmann transfer orbit. What condition are they in? I've got questions. First one is, what are they flying in? Second one, where are you in the solar cycle? Put another way, how likely are they to be hit by an X-class solar flare or coronal mass ejection or something else? How many people are going? Because if you're putting 2 people in a room for 9 months, I don't care how much they like each other, they're not both living. And that's just one way. So it's complicated to answer that. I hate that my default answer to everything is it's complicated. I actually got critiqued on that by professors in grad school. But it is. And it really matters, how do you intend to send them there? Yeah?
What are the first priorities for early settlement?
What are the first priorities for early settlement? I would say odds are figuring out a way to eat and breathe, maybe drink. Because those are the 3 things that'll kill you the fastest. Radiation would then come after that, because it's fairly easy to manage. You just have to dig a hole and bury yourself 8 meters down. But water, breathing, and eating are going to consume a lot of your time early on, just because we all need to eat, breathe, and drink. Otherwise, you die fast, faster, or really fast. Not in that order.
I'm trying to process all this, what you said.
Sorry, my talks have that effect.
No, it's not because it wasn't clear. The conclusion that I come to is you've come to a tremendous new ways of approaching things that can be done on Earth.
Yes.
From what you've done. And my question is, why don't you stop there?
So the question is, sorry, let me see if I rephrase this the right way. I've come up with a lot of ideas for ways we could improve things on Earth inspired by how hard it would be to do them on Mars. Well, why don't we stop there? Why don't we just figure out how to do them on Earth? I would love it if people were that forward-thinking. In my experience, and I believe history bears this out, we usually don't innovate until we have to. One of the reasons why I promote us trying to do things that are very hard is because then we have to. I'd love it if innovation happened without that driver, but it just doesn't seem to. It doesn't seem to be in human nature. That's one of the reasons why I want to push us on the edge of, hey, let's go do this thing that's nigh impossible, because then we'll actually sort it out. Put another way, show me someone who's doing it, and I will happily support them instead of space exploration. But since I don't really think that's happening in a serious way, I still want to push people to go do it.
expensive. I mean, I would take that money that I'm putting towards doing this on Mars and find a way to convince people that that's not the place to spend that money. Of course, that's not gonna work either, but it's sort of like, I don't like either. Nothing's easy.
The comment is, it's so expensive to do any of the things that I've just talked about. He would happily see that money placed towards things being done here on Earth. And I agree, except it doesn't seem to work out that way. We innovated medicine because of disease that was killing lots and lots of people, particularly children. We innovated better technologies for traveling across the oceans because we were traveling across the oceans and it was so hard. We innovated better ways to build houses because hurricanes knocked them down or earthquakes shook them apart. We as humans are reactive, not proactive. And so I don't think it's realistic to say, you've dreamed up these options, let's go do them. Because without someone that has to do it, odds are we're not gonna. That may be my cynicism or my optimism, depending upon your point of view, but that's my answer to that. Also, Mars is really neat.
Excess plastics, that we're helping. I mean, my father's a scientist, so I understand improving things, but it seems like we're taking the worst of things and dumping them someplace else in hopes that we can fix it and then we can improve ourselves here.
So the statement is that it feels like I'm taking all of Earth's current problems, from an excess of plastics, a lack of ability to make adequate food. I'd add in difficulties making sustainable power without messing up our environment locally or globally. Any number of these different problems and just dumping them on another planet. And that's a very fair objection. I completely agree with that. The reason why I keep being an advocate for space is because I think we can solve some of those problems before they become catastrophic here, which is when we'll be forced to deal with them here. This is a version of proactive planning, of saying let's invest in the things that will help present solutions before we need them, desperately need them here.
And then leave our garbage there, so we can improve ourselves.
And then leave our garbage on Mars. You know, I'd meant to not cite Kim Stanley Robinson in this discussion, but you remind me very much of the geologist of the mission in those fictional books, who is a preserve Mars because Mars itself is beautiful and do nothing with it. And I very much applaud and appreciate that spirit and that attitude. One of the things that you would have to do on Mars with regard to plastic is you'd have to figure out ways to reincorporate that plastic to eliminate the waste. And that's because every bit of hydrogen that went into those, or nitrogen, or anything else, is precious. And so you have to get good at plastic recycling, whether that's to make more plastic or strip it down to its base elements to get back what you put in. You have to get good at that on Mars, because the alternative is ship more in from another planet. And if you want to talk about a financial incentive to learn how to recycle plastic, if we had to ship it in from Mars, it would not be an abundant thing we dumped in landfills. So, I mean, my optimism is that it wouldn't be just trashing another planet, that it would be figuring out how to live with that planet in a sustainable way. But my cynicism has to cede your premise, which is we're currently working pretty hard to mess up the Earth. Can't we just fix that? And I agree with that. So I see you on both sides of this.
I thought it was interesting that the atmospheric chemistry was so valuable, and yet the dust seems so worthless. Why?
The atmospheric chemistry seems so valuable and the dust seems so worthless. Why? That's actually my fault as a presenter for not delving into that. The dust is actually fairly valuable if you're getting to chemical processes like what I talked about with Mars-Crete. So the fastest way to speed up a chemical reaction is to increase the surface area of your reactants. In plain English, grind it up, it reacts faster. Well, guess what Mars has? A whole lot of ground up rock. That's very chemically reactive. So that's where you would start with these weathering reactions is pick up the dust, put it in your reactor with a whole bunch of CO2, heat, and some water to help facilitate it. I'm not sure what other chemistry you would need. We haven't done this. And I'm sure that if you were doing this on Mars, you would figure out the details of how to make that work better. But the dust is going to be one of your most valuable resources to start with because it's pre-ground. You don't have to grind it. You don't have to do anything to it. You scoop it up and dump it in your reactor. We hope. All of this comes back to we hope. And that's because we're not currently doing it. So you're right. The dust is actually a very valuable resource and a major pain in the butt. And the fact that it's a valuable resource may help eliminate just how much of it is in your immediate surroundings with time. But you're talking about using up metric tons of dust to keep it away from your settlement. So it's going to be a while. Great question. These have all been great questions. Any more?
Can we capture asteroids and mine them to provide resources for this?
Can we capture asteroids and mine them to provide resources for this? I was about to accuse you of getting into another talk and not talking about Mars. And then you said, to help with this. It depends. So I could give a whole other talk on asteroid mining because that's some of how I got into planetary science is looking at different meteorite compositions, which tells us about asteroids. And there's a lot of really interesting science about what elements are where, what's accessible, how we would deal with that. And that might facilitate this. In fact, that might facilitate this very well. I mean, everything from grabbing iron asteroids to build space-bound craft that you didn't have to launch the building components for. But then you're talking about getting to an asteroid, mining it, smelting that, producing materials out of that, and then building something with it. That's a lot of infrastructure. I would love to see that. So yes, that would greatly help with sending people to Mars, with building Martian industry, with facilitating direct trade between Mars, Earth, and anywhere else that you happen to be in the solar system. But if you think this is complicated, try that. There's a lot that goes into it. So your answer is a yes, but.
Another question online, maybe two more after this
Okay.
one. What can we learn from the failure of the biosphere in Arizona?
What can we learn from the failure of the biosphere in Arizona? The first thing I would put on is it's really hard to balance ecology, particularly if you're making it yourself. That's the first thing I would learn. I'm not super familiar with the details of that, and I'm not an ecologist, so I shouldn't be super familiar with the details of that. But I think one of the root lessons is it has to be bigger than that. With a lot of these self-sustainability concepts that we've pushed on, it's fundamentally too small to house the level of complex ecology you need to keep it self-sustaining. And the problem with engineering your own ecosystem is nature is really messy. It's one of the reasons I didn't go into biology. Geology was messy enough. Any point of failure in that system means you have to introduce another system, which increases the complexity, which adds to what you have to maintain to keep going. I have a science fiction author friend that I enjoy batting some of these ideas around with, and introduced the notion of you might actually have an ocean ecology that you're dealing with to try to help balance things. So seafood might be present just because you needed a way to process all the ammonia waste and run that through into an ecology that you could then reintroduce the amides into your compost, to reintroduce it to your plants so that your plants aren't starving for nitrogen. And because plants aren't as good at dealing with ammonia waste, if you know what I mean. So it's a lot to balance, and I don't know the details because, again, I'm not an ecologist, but my understanding of its failure is it's fundamentally too small. As huge as it was, it's fundamentally too small. It didn't have enough aspects to really balance what was going on in a closed system ecology.
Speaking of science fiction, which is your favorite book?
Oh, speaking of science fiction, what is your favorite? I'm so tempted to cite Failure is Not an Option, but I think Gene Kranz would come after me because it's not science fiction. Anyway, I don't really have a favorite science fiction author, and it's...
Which is the most realistic?
Ooh, which is the most realistic science fiction author? How many gimmies do they get before you rule them out? Every time somebody goes to tell a story, especially in science fiction, they took some critical aspect about why it's hard and said, just give me this one. And the rest of it lets them tell a story. And I love science fiction for that, because it tells some amazing stories. I'm personally fond of The Martian. If you want a little more realistic TV show rather than book, Mars, which was put on by National Geographic, does a brilliant job of showing what it might look like to have an early settlement on Mars. But even there's a lot that they skip right past because they need to tell a story. Even though it's National Geographic and a quasi-documentary, they're still skipping past parts, which is great. That's storytelling. I love Star Trek because it tells some phenomenal stories and makes us look back at ourselves through its telling of science fiction. But they said, let's make power really simple. And then let's do everything with, we have way too much power. We can power whole suns and it's not a problem. Okay, great. That's a huge gimme. So there's a lot of science fiction I love. And that makes it really hard to say, well, what's my one favorite? In terms of recent science fiction, I really enjoy the Lady Astronaut books. They do an interesting what-if portrayal of, let's say, a meteorite landed on Earth. That would be a world-ending scale impact. Think Chicxulub and the death of the dinosaurs. Lands on top of Washington, D.C. in 1950. Good luck. It's a compelling set of stories. Again, there are parts they simplify and parts they don't. It gets a little messy in some places. And anyway, it's a great set of stories. Yeah. The Martian is another personal favorite. Sorry, I talk too much. I think we have time for one more. One more.
My question is, if you were stranded on Mars,
I'd die.
right, and you only had a choice of one mineral phase, would it be olivine because of its mantle vibes, or would you choose tritomite because then you could debate with the Curiosity team its silica anomalies?
I think your daughter helped you with this question. Context for the audience. This is the parent of one of my childhood friends who went on to be a geologist, and so he's asking me to pick a favorite mineral if I were stranded on Mars and needed one mineral to vibe with while I was there. And he even highlighted olivine because it's like the mantle, or tritomite because it's a silica polymorph, and there's a lot of debate, and the Curiosity rover is awesome. And I got to applaud, the Curiosity rover is awesome being thrown in there. If I'm stranded on Mars, I don't think I'm going to have enough time to debate what mineral phase I'm favorite of, because I'm pretty sure I just got put in a frosty vacuum and irradiated, and the radiation's the least of my problems. If I were living on Mars and had time for navel gazing and looking at mineralogy, I'd be really interested in looking at some of the sulfate species. And the reason why is because Curiosity, about a year and a half ago, I'm losing track a little bit, found within the sulfate unit some pure sulfur minerals. This was unexpected. On Earth, when we change to the oxidation state of something in nature, we often point at biology and say, "You did that, didn't you?" And more often than not on Earth, we're right. We don't have enough context in that particular case to say, did life do that? Now, the Perseverance rover found something similar but different different sulfate mineralogy that on Earth would say 95% of the time life did this. And the reason why planetary scientists aren't jumping up and down excitedly saying we found life is there's 5% of the time and we don't know what it means. I would love to look at those in more detail if I had time for that. And I were on Mars so I could access it. So I don't know, but probably neither tridymite nor olivine. I've stared at tridymite too much. Olivine's lovely but boring. Pyroxene would have been more compelling, but you'd have to go read my master's to find out why.
Okay.
Thanks, everyone.